As one of the most bizarre and perplexing phenomena in the universe, black holes continue to pique the interest of astrophysicists and scientists alike. These stellar entities, characterized by their immense gravitational pull and complete lack of radiated light, signify a boundary past which the established principles of physical science cease to function. Black holes were first proposed by Albert Einstein in 1916 as a byproduct of his general theory of relativity. Until the 20th century, when advancements in science made it possible to observe them indirectly, they remained purely conceptual. In the 1960s, when space travelers were looking at the Cygnus constellation, they accidentally came across an extraordinary astral body, a bright azure star that was emitting high-frequency X-rays. This was the turning point, until it was discovered to be gravitationally linked to the enormous black hole Cygnus X1. This star's revolving around an unseen partner defied conventional explanations. The discovery of Cygnus X1 marked the beginning of a new era in the investigation of these astronomical mysteries and provided definitive confirmation of the existence of black holes. Cygnus X1, situated approximately 6,000 light-years from our planet, possesses astonishing attributes. It exerts a gravitational attraction so strong that even photons are unable to escape its grip, despite its incredible compactness. It was given the name black hole because of this characteristic, which sums up the essence of these enigmatic formations. Despite their opaque nature, which makes direct observation difficult, subsequent research has revealed a large number of black holes dispersed throughout the universe, with estimates suggesting that our Milky Way galaxy alone may contain up to 100 million black holes. Several potential black holes in our galaxy have been identified by space scientists. These range from supermassive black holes that reside in the nuclei of galaxies to stellar mass black holes that originate from the debris of massive stars. The gravitational reach of black holes stretches well beyond their nearby zones, influencing the formation of celestial arrangements and affecting the destiny of adjacent material. The fate of anything that gets too close to a black hole is determined by its unwavering power. They are inevitably pulled toward the event horizon, the terminal frontier, where they undergo intense tidal stresses and are eventually devoured by the singularity at the center. This dramatic event, referred to as spaghettification, is the ultimate display of a black hole's gravitational dominance. An object's gravitational dispersion along its length becomes so extreme as it approaches the event horizon that it becomes elongated and twisted into a string-like shape resembling noodles. The object's cohesive forces are overwhelmed by the black hole's forces, which cause it to break up into a stream of particles that eventually join the singularity. Black holes remain shrouded in mystery, despite their compelling appeal as natural laboratories for investigating the extremes of physics. A desire to comprehend the fundamental nature of space-time and gravity drives the ongoing effort to decipher their secrets. Black holes act as unobtrusive guardians in the vast expanse of space, encouraging humanity to explore the unknown and challenge our collective wisdom. Though we are separated from the closest black hole by an enormous span, roughly 2,500 light-years, questions and apprehensions regarding their possible effects linger. In 2021, investigators attained a historic milestone by securing the inaugural clear depiction of a black hole, namely M87, positioned at the heart of the M87 galaxy. This outstanding accomplishment offered essential understanding into the characteristics of black holes and their elusive architecture. The visual findings disclosed that black holes consist of intricate strata, disputing the old notion of them as isolated voids. Within a black hole, researchers are able to distinguish three distinct layers through precise examination and image compilation. The outermost stratum is the event horizon, a crucial border indicating the irreversible threshold. Once an entity surpasses this boundary, gravity becomes overpowering, ensuring its unavoidable descent into the black hole's abyss. Advancing inward, the photon sphere constitutes the secondary layer, where light encircles the black hole in constant entrapment. The dominant gravitational force binds any light particles that enter this region, keeping them forever trapped in the black hole's cosmic grasp. The singularity, the third and final layer of the black hole, is where physics conventions break, down at the nucleus. Scientists now find themselves in a state of profound ambiguity and hypothetical contemplation as the universe's known laws cease to operate. The intricacy of black holes and their inherent unpredictability pose serious obstacles to our comprehension. Each black hole has distinct characteristics and patterns that defy easy classification, despite their tri-layer configuration. As a result, innovative approaches are required to unravel the complexities of these cosmic titans because conventional scientific methods are inadequate for the task. Black hole research continues to be dominated by indirect monitoring. Any attempt to send probes into black holes would unavoidably result in their destruction as a result of the overwhelming gravitational pull, which makes simple examination impossible due to the enormous challenges posed by their gravity. Nonetheless, scientists persist in their determination to unveil the enigmas of these vast cosmic entities. Diverse hypotheses, from stellar implosion to interstellar mechanics, offer tantalizing insights into their beginnings and functions. Notably, NASA's examination of M87's central galaxy provided convincing evidence of a supermassive black hole ruling vast cosmic regions. The natural inquisitiveness and thirst for enlightenment of humans propel the pursuit of truth forward in spite of these obstacles. Despite the fact that black holes may not be easy to understand, the unwavering commitment to scientific research holds promise to shed light on the darkest regions of the universe and decipher the significant mysteries within. Roy Kerr's pioneering. Research in 1963 introduced a revolutionary angle on black holes, suggesting a groundbreaking model of rotating black holes that opposed standard interpretations. Central to Kerr's framework was the idea of the ergosphere, a surrounding zone where opposing forces stabilize gravitational implosion, hindering further internal collapse. This innovative region demonstrated intriguing deviations from standard models. Physics refers to the intricate puzzles contained within black holes. However, the most captivating result of Kerr's proposal was the anticipation of an Einstein-Rosen bridge, colloquially called a wormhole. This speculative formation signifies a possible corridor through space-time, providing a link between far-off sectors of the cosmos or even alternate dimensions. The subtle interplay between reality and Einstein's general relativity is the basis for the concept of wormholes. In this model, reality is interwoven into a four-dimensional matrix dubbed space-time. Massive bodies distort this matrix, forming gravitational fields that direct the motion of nearby objects. Wormholes effectively function as shortcuts within this universal matrix, connecting distant sites in space-time and, theoretically, allowing swift passage over immense spatial spans. Still, the endurance and feasibility of wormholes remain central, topics of rigorous debate and reflection among theoretical scientists. Though the potential presence of wormholes sparks dazzling visions of interstellar journeys and temporal exploration, considerable hurdles and constraints temper these extraordinary aspirations. The fundamental instability of wormholes, compounded by the daunting effects of quantum phenomena and radiation, raises doubts about their practical use as methods of travel. Moreover, Einstein's theory imposes essential limits on speed within spacetime, implying that even if stable wormholes were real, they might not permit transit faster than light, a hallmark of many science fiction stories. Despite these concerns, wormholes remain a fascination as a symbol of scientific ambition and discovery. The concept of the wormhole, named for its trailblazing originator, encapsulates the compelling idea of cosmic gateways and alternative realms, prompting humankind to explore the vast riddles of existence and imagine the endless opportunities that lie ahead. The effort to develop a unified theory that bridges the seemingly incompatible worlds of gravity and quantum physics has driven the search for a theory of everything, a holistic model capable of including all basic forces and components in nature. At the vanguard of this mission stands the acclaimed physicist Miyoku, whose pioneering achievements have advanced the study of superstring theory. Superstring theory marks a bold shift from conventional frameworks, asserting that elementary units are not 0 points, but rather minuscule vibrating strands. These strands, akin to the strings of a musical instrument, vibrate at distinct pitches, giving rise to the various particles and energies we observe in the cosmos. In this worldview, the universe resembles a majestic symphony, with each particle representing a distinct harmonic tone of these fundamental strings. One of the most notable outcomes of superstring theory is its capacity to describe the puzzling features related to black holes, wormholes, and other extraordinary solutions to Einstein's gravitational equations. Gravitational singularities and topological oddities are the result of the dynamic activity of these strings as they move through the fabric of space and time. Yet, the refinement of superstring theory hides its deep intricacy, as it demands the presence of more dimensions beyond our standard 3 dimensions of space and 1 of time. These extra dimensions, unseen by direct observation, create a significant challenge to human perception. Nonetheless, illustrative models, like comparing our world to fish living on a 2-dimensional surface, offer a glimpse into the elusive essence of these elevated dimensions. Their compact nature, similar to a paper tightly rolled, makes them undetectable in everyday experience. Yet their influence saturates the framework of reality. Although the accurate configuration of these secret dimensions remains obscure, their theoretical existence provides a compelling rationale for the elaborate designs and irregularities present in the universe. Additionally, the mathematical core of superstring theory has sparked a renaissance in mathematical physics, uncovering powerful ties between shifting numerical patterns and natural behavior. Indeed, the journey toward a theory of everything has fused disciplines together, illuminating the intricate bond between numbers and the physical world. While its theoretical beauty and scientific potential shine, superstring theory is still an unproven hypothesis waiting for tangible proof. The hidden nature of extra dimensions presents a daunting blockade to experimental confirmation, keeping the theory within the domain of speculative math. Nevertheless, the daring vision of superstring theory continues to inspire both scholars and dreamers, inviting humanity to dive into an adventure of mental exploration. As we advance into the frontier of theoretical physics, led by the brilliant light of superstring theory, we stand at the brink of a new chapter in cosmic comprehension. The endeavor to solve the conundrum of quantum black holes has long challenged researchers, symbolizing a massive barrier to our grasp of the essence of the cosmos. Despite countless attempts to decode this puzzle, a complete solution has eluded us, prompting Edward Witten of the Institute for Advanced Study at Princeton to label superstring theory as 21st century physics that accidentally landed in the 20th century. However, newer breakthroughs have injected optimism into this pursuit. Various research teams have separately announced key progress, showing that string theory might yield a total solution, albeit in a restricted setting of 2 dimensions, not the full 10-dimensional system proposed by traditional superstring theory. Although this step forward is promising, the path to a full resolution is still under construction, with many complexities lying ahead. The aspiration to discover a unifying theory of everything calls us to investigate the deepest layers of the cosmos, where the separation between reality and abstraction dissolves, and the truths of existence lie in wait. The examination of black holes holds immense meaning for our perception of the universe, confronting our beliefs about what is real and posing fundamental questions regarding the core of existence itself. The intricate dynamics at work in the stars are revealed by the synergy between black holes and other space phenomena, like neutron stars and gamma-ray emissions.